Cadence, so I suck at physics, but because I studied, I'm good. Let's draw F.
And
You're dead.
Let's continue. Okay, so I'm going to draw the applied force, which I'll label F to respect the diagram. Then I'm going to draw the kinetic force, kinetic friction force, which will be smaller because it's, kinetic friction, meaning it's in motion. So it'll always be smaller, but I can't scale it exactly because the force is always changing with respect to time. Well, as a function of time. Now I need to draw FG because it's on the surface, so it's going to exert its weight. I don't know what that is. And then I draw Fn, the reaction force, which is equal to that. Yeah, so that's my free body diagram. And now I calculate the kinetic friction force. Fk is equal to K is equal to uk times n. Uk times Fn, right? Well, what's Fn? Well, the magnitude of Fn, because it's on a flat surface, equal to Fg. Flat, horizontal surface, like parallel, not a ramp or anything. Right? So that's 44.5 newtons, as the problem gives us. That's going to be equal to Fn. So, plug that in. K is 0.2, as given by the problem. And then Fn is 44.5 newtons, not 45. And that's equal to 8.9. Good, because it's opposing our line of motion. Positive, it's negative. Okay, for C, they want an expression for dx dt. So let's go over here. Okay, for C, they want an expression for dx dt. Well, I know that dx dt, the change in position over the change in time, looks like delta x over delta t, is going to equal velocity as a function of time. Right? Now to get velocity as a function of time, I'm going to need to integrate acceleration as a function of time with respect to time. And that gets me velocity as a function of time. Well, how do I get a of t? Well, I know that my net force in the x direction is going to be equal to m times a, right? X direction because I don't even need to care about the y direction, nothing's happening. So really I could just write sigma f. Anyways, that's going to get me mass times accel, right? Well, what is my net force? So I have the force in one direction, 8t squared, the forwards direction, minus my friction force, 8.9. And that over m is going to give me acceleration, right? But it's as a function of time. Accel isn't constant because this applied force right here is also a function of time. So, as this changes, the acceleration also changes. That's why this can become a function of time. So, let's simplify it. 8t squared minus 8.9 over m. Well, what's m? Well, actually, the weight is 44.5 newtons, Fg. Right? And I know that Fg is equal to mg. Correct? So if I do Fg over g, 44.5 newtons, over g, which is magnitude 9.8 meters per second squared, that gets me my mass, which equates to 4.54 kilograms. So, bye-bye, 4.54 kilograms. And that simplifies to 1.76 t squared minus 1.96 is equal to a of t. Now I'm going to integrate. I'm going to integrate a of t, which is just that function up there, with respect to time. And that's going to get me v of t. Well, let's integrate it. I'm going to add 1 to the exponent and divide by that new exponent. So I'm going to get 1.76 t cubed over 3. And then for this one, I'm just going to multiply this by t, because if I took the derivative of that, that's going to get me 1.96. So 96t. And then since there's no bounds, I'm going to need a plus c. That's going to equal v of t. Well, what is c? Well, I know that the initial speed of the block is 4 meters per second, right? And that means v of 0 is going to equal 4. Well, if I plug in 0 here and 0 here, these just turn into 0. They're negligible. So that means c is equal to 4. So that's what I'm going to change my c into. 4. And this is my v of t function. This is in meters per second. So I can just parentheses this, I guess, and then show meters per second. And this is also in meters per second. Now, that's my velocity function, v of t. Now, the magnitude of the instantaneous velocity when t equals 2. So that's going to be part D. So basically, I want the magnitude of the instantaneous velocity at 2, right? So that's really going to equal to whatever I have here, because this is my velocity function at 2. Right? And then this is also going to be magnitude of whatever this inner solution is. So let's solve for that. And that's going to get me 4.77 meters per second. And that's the magnitude of the instantaneous velocity at 2. Oh, that's so E. Now E, and what's the instantaneous speed of the block when it's at position xt equals 2m? So immediately, when it says x of t equals 2m, I know I need an x of t function. Well, how do I find that? I can integrate v of t with respect to t to get x of t. So let's do that. I'm going to get my v of t function. I'm going to bring it down. Right? And I'm going to simplify this to ease the integration. Make it easier on the eyes. So this turns into 0.586. Yeah, 0.586t cubed. This turns minus 1.96t plus 4, and this is still v of t. Now I'm going to integrate it to get x of t. Integrate with respect to time. Well, once again, I'm going to add to the exponent and then divide by that exponent. So 0.586 t to the power of 4. Let's make that 6 a little nicer. Over 4 minus 1.96t plus, oh no, once again, add the exponent and divide by whatever that new exponent is, over 2, and plus 4 times t, once again, because if I take derivative of this, it gets me back to 4, and the integral is just reversing the derivative, plus c. It's going to be equal to x of t. Now going off the problem, what the problem gives us, x of t is equal to 0. So, if I mean, no, not x of t equals 0. X of t equals 0 is 0. So basically, the initial position is 0. So basically, if I plug 0 into for all of this, right, then c is supposed to equal 0. So I know that c equals 0 because the initial position is 0. So this is my x of t function. Now let's simplify that. 0.1465 t to the power 4 minus 0.98 t squared plus 4t is equal to x of t. Right? And x of t equals 2 meters. Graphing this at time equals 0.58 seconds. Right? And just to clarify, this is a function meters in meters. Same here. In meters. So yeah, with this information, I need to find the velocity when it's at position x of t equals 2 meters. Well, when is it at position x of t equals 2 meters? At this time. So what do I do with this time? I plug it into the velocity function, but the absolute value of it to find speed. So the value of velocity at 0.58 seconds is going to equal, well, where's my velocity function? Right here. There's this, and then simplify down. So I'm going to bring that down. And that's at 0.58. Right? And when I solve that, that gets me the speed at where the position is 2 meters to be 2.978 meters per second. So yeah. Alright, F. They want the average speed for the entire 8 seconds of motion, right? So I know that speed is the absolute value of velocity, right? So if I integrate the speed, then basically I'm just getting the distance traveled from 0 to 8 seconds. And distance traveled 0 to 8 seconds over the time frame, that's just going to be my average speed because speed is distance over time. So that gets me 71.296 meters per second. Great. G. On the grid below, graph the velocity block as a function of time. So let's label my axis. My y-axis is going to be velocity in meters per second. My x-axis is going to be time in seconds, right? And let's label my values. So I'm going to go off the seconds of motion. So 0, you have 2, 4, 6, 8. And then for my x-axis, we go 40, 80, 120, 160, 200, 240, 280, and 320. Okay, let's start. As x is 0, y is 4, so put a dot there. And x is 1, y is actually a little bit smaller, so around here it's going to be like 2.6. And x is 2, y is back to where it was at like 4 or so. 4.76 this time actually, so it's a little higher than before. X equals 3. Now it's around 13, so make it a little bit higher. X equals 4. Now it's at 33. X equals 5. Now it's at 67. X equals 6. Now it's at 119. X equals 7. Now it's at 191. And x equals 8. Now it's at 288. Like so. And then graph it out. Include these negatives in case you can't sort of long. Here you go. And there you go.